Welcome to the presentation for paper ID 737, Spatially Aware Metadata for Raw Reconstruction. I am Abhijit Punnapurath and this is joint work with Michael Brown. When we take a photo, the image that we see on the screen is the processed output of the camera. The image signal processor, or the ISP, is dedicated hardware present on board the camera that renders the raw sensor image to the final display referred output of the camera. The ISP applies a lot of processing steps to convert the raw sensor image to the final display referred output. Among these processing steps, local tone mapping is one of the most important operations used to enhance the overall appearance of the final rendered sRGB image. Unlike a global tone mapping operator that modifies a pixel's intensity the same regardless of its spatial location, local tone map operators dynamically modify the tone mapping operator to enhance contrast in a spatially varying manner. Local tone mapping has a significant impact on the rendered sRGB image's final appearance. It's often desirable to revert or de-render the sRGB image back to the original raw sensor image. However, this is a very challenging task because many of the operations performed by the ISP, including local tone mapping, are non-linear and difficult to invert. Existing raw reconstruction methods ignore local tone mapping and assume that a global transformation exists between the raw RGB and sRGB color spaces. In this work, we advocate a spatially aware raw reconstruction method that is robust to local tone mapping and yields significantly higher raw reconstruction accuracy compared to existing raw reconstruction methods. Here, we describe how our method works at capture time. We sample the demosaiced raw RGB sensor image on a sparse uniform grid. These raw RGB samples are then stored as additional metadata along with the ISP rendered sRGB image. The samples constitute only 0.2% of the full-sized image and add only a nominal overhead of 96 kilobytes. Let us now examine how these samples are used during the editing stage. To edit the image post-capture, we first recover the raw RGB samples from the saved metadata. We also sample the sRGB image at the same spatial locations. From these corresponding raw sRGB samples, we estimate a de-rendering function that considers the RGB intensities as well as their spatial locations X and Y. This lends our method robustness to the local tone mapping operation applied by the ISP. Applying the de-rendering function on the sRGB image produces our estimated raw RGB image. We implement the de-rendering function as a scatter point interpolant using radial basis functions. Please see our paper for details. We now evaluate our method's raw reconstruction performance. We compare against two blind raw reconstruction methods that do not use additional metadata, two metadata-assisted de-rendering methods, and a baseline variant of our method that uses the same metadata samples but discards spatial information. It can be observed from the last two columns that our proposed method more closely matches the ground truth and has the lowest reconstruction error. Please refer to our paper for experiments demonstrating our method's usefulness on a number of computer vision and photographic applications. To conclude, we presented a spatially aware raw reconstruction method that is robust to local tone mapping. Our approach is easily integrable to existing ISP hardware, has low computational overhead at capture time, and requires only 96 kilobytes of additional metadata.